All right, so I'm going to talk about how to add real-time push to your API. So if you've got a REST API and folks are polling it over and over, you should probably add some kind of push. So let's talk about what that means. So first of all, real-time is kind of an overloaded term, so I'll define it now. So for better or for worse in the web community, when we say real-time, we're often talking about push and not necessarily latency or time constraints or anything like that. So you can think of real-time being useful for chatting or games or news. Anytime you need the screen to update to show new content to a user. Sometimes this is called near real-time because it's often over TCP instead of UDP, so it's might be lagged a little bit, but it's being pushed at you is the main point. Do you need real-time? You do. The most popular apps have it these days. If you've got a new type of product, it's a great way to add some flash to it. Users are expecting it. Now, what about real-time APIs though? Most APIs are like REST. They don't have push. Do APIs need to be real-time? They do. Some of them are actually already, like Twitter, for example. And I'm a big believer of APIs sort of taking over the world and everything will be API connected. And so if APIs are the future of everything, then they better have some kind of push, right? Otherwise, all of our apps are suddenly going to lose push. So we need to somehow make sure that there's push in our APIs. So briefly about me, so I run a company called Fanout where we help people with real-time push and APIs. Before that, I was the CTO at Livefyre, dealing with their large-scale commenting system. So I kind of observed the problems of developing a push system there and then wanted to make something that others could use. I'm also just a big fan of like open standards and federation and stuff. I was involved in XMPP, the RFCs, years ago. So, all right, so how do real-time APIs work? So typically, you have some kind of long-lived TCP connection. You're not dealing with UDP. It's pretty much all TCP-based. And what you see in the wild are unconventional uses of HTTP, so things like an HTTP stream, for example, like a stream that never ends. Or you're using WebSockets, some kind of non-HTTP protocol. And that's pretty much what people use. So what you see out there is I have these 4 categories. HTTP streaming, that's where a response never ends. HTTP long polling, that's where the server hangs the request open, but it does deliver a complete response when it's done. WebSockets, of course, that's like the most cutting edge. And then you also see webhooks. And pretty much every API you see out there that has real-time is going to be based on one of these 4 mechanisms, or multiple sometimes. And so what I'm going to do in this talk is sort of go over how each of these work using real-world examples that you've probably seen, and then get into sort of how you can make something like this and how we can make it easier to build something like this. So first of all, HTTP streaming. So you have this response that never ends. The content is usually lines. Sometimes it's lines of JSON. Sometimes it's just lines of text. Depends on what you're doing. Server-side events is also a very popular format because it's compatible with browsers. So if you're using JavaScript and event source, you can consume a stream that way. Server-side events is actually a multi-line format, but it's still lines of text. So for example, here's how Twitter's streaming API works. So you make a GET request to some endpoint. You provide OAuth credentials, so it's very similar to how you might deal with their REST API. The difference, though, is that this request is never going to end. You end up with a response that looks like this. So you have, there's no content length. The transfer encoding is chunked. And each tweet is a JSON payload that's all in one line. So it's not pre-printed. That way they can use new lines as a delimiter. And so, yeah, so this is how it works, and it's push. Twitter's not the only one to do it this way. I found out that Gitter does this. We use Gitter for our chat. Thought it was pretty cool that they're doing that too. So what's good about HTTP streaming? Well, it's HTTP, so you probably understand it pretty well. It's also fast, so unlike maybe like long polling, for example, there's no issues with sending a lot of data quickly to a recipient. It's literally just a TCP packet once you've got the connection open. The drawback, though, is it's only one direction once it's open, so it's not bidirectional like a WebSocket. So and generally speaking, the reason you might need to talk back to the server is because you want to listen to something else, like maybe there's different data sources. That will always involve opening a new connection if you're using HTTP streaming. But if you don't do that very often, then it could be worth it to use HTTP streaming. So long polling is a little bit different. This is where the server has a delayed response. So you make a GET request and the server just holds it open, maybe for 30 seconds or 2 minutes or whatever. And then it either responds with new data at some point or a timeout, some kind of timeout data saying that there's nothing yet. And then the client just opens a new request after that. So this is just straight up HTTP. It's just the server's holding the connection open. Amazon SQS uses long polling. So for example, if you want to, you don't want to poll a queue to find out if there's new items, if you want to just wait for an item, you can actually pass this wait time seconds query parameter, and that'll tell their server to just hang open for 10 seconds. And you can probably set that value higher. And then once there's data, you get this, you get a push. But the push looks just like a regular response. Like they look identical. And this is, Amazon's XML format. They're not the only ones doing long polling either. Dropbox notably does that as well. And we also implemented long polling at Livefyre when we were doing, especially the browser connections to the comments. So what's good about long polling? Well, it's RESTful. You can actually literally document a long polling API probably with Swagger or something, and it'll fit because you're not having to do something weird with some kind of long stream. It's also sort of naturally reliable because of the periodic requests. So if you generally won't lose data with a long polling API. The client will make a new request and then everything will self-heal. Your IP address changes, it'll self-heal. So long polling is pretty resilient, sort of without any effort. Whereas with something like a WebSocket, you actually do have to remember to track timeouts and send keep alives and basically essentially replicate a lot of what you would do with long polling anyway to have reliability. Downside of long polling though is that once you've sent something to the client, the connection is closed, or the request is ended. The connection can still stay open though. But you can't send again until the client makes a new request, so it's not great for continuous push. You would not want to make a collaborative drawing application that has pixel accuracy with long polling. That would be horrible. And then there's also WebSockets. So this is the new game in town, relatively. You get a bidirectional message channel. It's also supported everywhere by now, so I wouldn't worry about if WebSockets will be supported. Pretty much everything has it. Here's how blockchain's API works. So you make a request to this INV endpoint. I'm actually not even sure what that stands for, but that's where they emit their information about, I guess, Bitcoin transactions. And so WebSocket starts out with what looks like an HTTP negotiation, but it responds with a code 101. So that's how you know to go into this bidirectional stream. And then once you've got that bidirectional stream, then you actually exchange messages. And so in the case of blockchain, they have this sort of RPC protocol they've designed. So the client sends some JSON saying, I want to listen to blocks. And then the server says, here's a block when something happens. That's their own kind of message format. And since it also is encapsulated, you don't need pretty printing. Or I'm sorry, it's OK to have pretty printing actually in the payloads. So WebSockets are very popular among Bitcoin companies for some reason. Slack's API is also WebSockets based, if you read their docs. I'm going to bring up CBIX later too, because actually they use the pushpin approach, which I'm going to talk about next. So great thing about WebSockets is bidirectional. It's pretty much the best technology that you can use. There's also no browser connection limits. That's kind of a funny advantage. I don't know why that's the case. Maybe somebody forgot to put the code in there, but it's not limited like HTTP is. So woohoo. It's kind of a weird choice for APIs though. Most people are still familiar with HTTP. So I would advise if you did use WebSockets as an API, as literally something you're going to tell your own users to consume, you might want to have something else as well, just so it's not too super weird. You don't have status codes or headers, so all that kind of RESTful fun stuff is missing. You kind of have to make it again. And finally, there's webhooks. This is probably the easiest one of all. This is where the server makes an HTTP request to the receiver. No long-lived connections, and you just register a URL in advance. So GitHub uses webhooks. And so, for example, if you want to listen on for when a new issue is posted, this is how you would do it. You'd register a callback. In this case, I'm registering example.com/target down there in the config. And then there's multi-steps here. So GitHub says, OK, we've created the registration for the webhook, and it actually makes a URL to represent the registration there, that hook/1. So you can actually delete it later. That's how you'd unregister. And then when an event happens, it does a post to that endpoint to that example.com/target. So webhooks are very popular. Stripe uses webhooks, Facebook. The great thing about webhooks is that it's so simple. It's almost so simple that it doesn't even seem like you need tooling. Everybody can make an HTTP request, so you could just throw that right into your backend code right now. Downside though is only servers can receive data, so it's not quite as useful as the others. And it's also hard to test because you actually need a server to test it. So you can't just like curl an endpoint to see what happens. You need to open up a port somewhere. You sometimes have to set up like a reverse proxy. It's a little funky. All right, so there's all these choices: long point streaming, WebSockets, webhooks. What do you use? It's up to you, really. I think they're all valid for different reasons. Some companies use more than one. Like I mentioned, Dropbox uses long polling, but they also use webhooks. I'd say if you had to pick just one, like you just couldn't spend time on more than one, HTTP streaming is a good compromise because it's very fast, but it's still familiar. If you want something literally today, just do webhooks. That's pretty easy. Worry about client connections later. All right, so how are you going to build an API like this? And I'm not going to talk about webhooks because that one's a little bit easier. But for the client-oriented ones, what can you do? So there's a bunch of real-time solutions out there. Everybody's trying to solve real-time push in a bunch of different ways. You probably recognize some of these names on this slide. Most of them are end-to-end, so you get a client library with them. So if you use Pusher, you have Pusher's client library. It connects to Pusher's domain name. It would be an odd choice for a API. And so with an API, you have your API contract, and it's something you own, and it's not some kind of secret or private protocol. And so you need something a little different, unfortunately, than the kind of stuff you're used to. And in fact, when you do see an API out there that's real time, like any of those like 20 or however many companies I mentioned earlier, like Slack and Twitter and whatnot, this is all custom. Nobody's using something off the shelf. And it's really just because nothing's been made to address the needs of APIs. And you really don't want to be coding on something like this just because it's so easy to get wrong. I did that at Livefyre. You have this like big stateful server. It's got thousands of people connected to it. You get one thing wrong and everybody gets disconnected. Like you don't want to be touching this thing very often. So it'd be great to just use something that existed. But you're building an API, and too bad. You don't get to use anything. Unfortunately, though, that's not actually the case. So there are some solutions appearing now. So I am going to talk about pushpin. That's the project that I'm working on. There is another one, though, called streamdata.io, which you can check out as well. These are both solutions for APIs. They're actually also both proxying type solutions. So the assumption is that you have some kind of API backend that you're going to hook this to. But API solutions are showing up, so that's good. So now I want to talk about pushpin and how you can actually use this to make an API. So pushpin is a proxy, and it has some real-time magic. So it can handle long-lived connections, WebSockets, HTTP, and you get full control over the interface between the client and the edge. So this is what's unique about the project. There's no pushpin client library. The client library is, it's something you can make if you want, or maybe not. Well, some API providers don't even have client libraries. It's kind of your call. You just get to decide what your API should be, and then you can use pushpin to make it. And it's also open source, so it's on GitHub. You can check it out. Before I get into sort of how it works, I just want to show you what code looks like. So here's an example of Django. There's a lot of magic happening in these few lines of code, but essentially, pushpin is sitting in front of Django, managing the long-lived connections. If you've declared this endpoint, pretty much all you need to do is flag an incoming request as something that should be dealt with in a push way. So for example, set hold stream flags the request as a streaming connection that never ends. You can assign one or more channels. Here we're associating my channel with the incoming request. When you respond on this endpoint, the body data and headers provided are sent as initial content to the client. So what the client will end up seeing is stream opened with a new line, and it'll be text plain as the content type, but it'll hang open after this. And then finally, when there's data to publish on a channel, you can just call publish in one line of code and send it down. So How does this actually work, though? So getting into pushpin, what we wanted to do here is separate. There's these different roles when you're building an API, different tiers in an architecture that kind of got lost a little bit with the way push works. So typically, if you're building an API, you have your API designer, you have your backend implementer, you have maybe your DevOps dealing with caching layers, you have your clients developing client code against the API that was defined first. But as I mentioned earlier, the way real-time push tends to be solved is these solutions are all end-to-end. So it's kind of like it encroaches on every single layer there. And so we want to kind of break that apart so that people have the roles that they should have in this project, and get some standardization and some interop in place. So here's how I view the real-time API process. So first, you come up with your API. You come down from the mountain and say, this is how you will be accessing our live data. And then your engineers get to work. They implement this spec. But you made the spec first. That's the key thing, which is different than something like Socket.io, where they've already made the spec for you. So the idea here is you've made the spec first. Now, how are you going to implement it? Now, if you're Twitter, this is where the story ends, because you actually just do the whole thing yourself in the back end. But it would be nice if there was some of this work you could pass off. And so that's where this pushpin proxy server fits in. So you stick it in front of your backend server, and it handles all the long-lived connections so that your backend doesn't have to. This means that your backend can actually be a thread pool-based system like Django. Like normally Django would be the worst system to do a push architecture with, but when you've got something like pushpin in front, then it becomes okay. We wanted to make an open integration protocol between pushpin and the backend. So the idea here is that you don't code to pushpin. You code to something called grip, which I'll talk about in a moment. But the intent here is similar to the standardization that's occurred in the caching world, where you have cache control headers. You don't code to Varnish or Cloudflare. You code to caching standards or ways of developing. And that way, DevOps has some freedom there. And then so once you've built this API using pushpin, for example, now your clients can then speak to this API you built using the API that was defined. And what's key about this is that the clients don't know that pushpin exists. Again, there's no pushpin client library. It's pretty much a detail of the DevOps engineering decisions being made over there. And the theory here is that now we have all those roles that a typical API team has. They're restored now, but just in a push context. And you also have the different pieces of architecture in place, and there's some agility. You can actually rewrite the backend. Say it's Django and you want to change it to Rails. Sure, pushpin is still pushpin, clients are still clients, the API hasn't changed. Let's say you want to replace pushpin and move to a cloud service or something. So we host a cloud service version of that. And that could be a DevOps choice. There's no engineering involved in that decision. Just like there's no engineering involved typically with changing between Squid and Fastly. So basically, this brings push development to the same level of sophistication that we've already achieved with pull. And that's great for DevOps because they can go to bed easy. Nobody's redeploying pushpin constantly. So that whole issue of one line of code crashes and you lose thousands of connections, that's not going to happen because you're not messing with that. Your backend's going to crash all the time, but that's okay. So a little bit about grip. This was that open backend protocol that I mentioned. The idea here was just to give it a different name to sort of de-vendorize, de-brand it, so that, again, so it can be a standard. It stands for Generic Real-Time Intermediary Protocol. And so the engineers target grip. So you may have remembered on that initial slide with the Django example, there was the word grip in a couple of places maybe, instead of pushpin. That's why. And then this, again, gives DevOps the freedom to decide what actually occurs in that middle layer. So to go through the flow of how this works, you can probably imagine how this works already actually with the descriptions I've given, but here's a sequence diagram just so it's super clear. So a client makes a request to the proxy. The proxy forwards the request to the backend, and this is pretty much forwarded as is. So if there's a cookie or authentication header, it's all there. Pushpin does add another header, so you know that it came from pushpin. But other than that, it's a regular request. And then when you reply, you can reply with special instructions, and that'll tell pushpin to hold the connection open. And so once you've replied, the transaction between pushpin and the backend is complete. but the request between the client and pushpin remains open. So if you had a streaming connection, it's now open, being held for updates. And then at some future point, your backend can push data to pushpin. And this is done using an HTTP post or 0MQ. We have a couple of inputs that you can use there, which then pushpin can then inject into one or more open connections for receiving. And then that's basically it of how it works. So let's get into the details. So Grip supports both HTTP and WebSockets. Now in the case of HTTP, there's two modes. There's streaming mode and response mode. Response mode is long polling. And they both behave a little bit differently. So with streaming, at instruction subscribe time, you specify a partial response that the user should see immediately upon connection. So they get this like initial status code headers, some initial body, but then it hangs open at that point. And then when you publish, you actually publish chunks of body such that it, you're just appending to this stream that's already open. Response mode is much different. In this case, there's no initial response because with long polling, you actually send an entire response at publish time. So when you set up a response mode subscription, you just specify the timeout response. So what should pushpin use if you don't send any data in time? And then when you publish data, you actually publish the entire payload, status code, body and all. And so here's how it like really looks. So if your backend responds with these two extra grip headers, grip hold and grip channel, this is saying hold this connection open as a stream, bind it to this channel. And here's some initial data that should be sent down. And then when you want to publish, you just post to this publish endpoint. It's on a private port for pushpin, so you wouldn't let outsiders have access to this. And you just say, on this channel, I have this content that I want to send to anybody that's an HTTP stream. And that's how you publish data. So I think the best way to understand this is to actually just try it. So let's see if I can, you guys can see my screen here. I like to do this in a VM. Let's see, yeah, can I do? Is that pretty readable? Okay, so I have pushpin in here. It's just a git checkout, so I can just run it from the directory. The most notable thing here to know is that it's listening on port 7999 as the input port. So let me get a new terminal. Increase the size of this. All right, so I have Apache running on this box as well. So here's the. I'm actually going to do a demo with Apache and PHP because I feel like it's kind of, you wouldn't expect to use that for real-time push. So here's the configuration for pushpin. It's super simple. The asterisk means any input. So we're just saying everything that comes to pushpin port 7999, whether it's an HTTP request or a WebSocket, forward it to port 80 on the local machine. The over HTTP flag over there means to convert WebSockets into HTTP requests, which is another kind of fancy thing you can do with this. And I'm going to talk about that later, but this is the basic routing setup. And so I've got some scripts in the Apache directory. Let's see. So hopefully you guys understand PHP, or at least you can figure it out. So what this script would do is if you were to make a request to this endpoint, it would set these headers. And then the body is just like floating text, because you can do that in PHP. So for example, if I actually request this on the local machine, I get this, which is what you would expect. So you can see that those headers are being sent back properly. So now, what if we connect through the proxy? What do you think will happen? So the request is hanging open now. And what has happened is pushpin interpreted those grip headers. It also stripped them away so that the user doesn't actually see those. That's actually another interesting thing about pushpin is that the channel schema and the negotiation is all backend. Client doesn't even know it's participating in pub/sub here. Content length is also gone. It's been replaced by chunked encoding. And it's just hanging open. So then we can publish to it. So I'll open on a separate terminal here. And all you have to do is send a post request to the internal port, which is 5561. So you can kind of see this line of code. This is just a curl command, and it's publishing using that JSON format I showed earlier. Here's like the HTTP stream section of it, but it's also at the same time publishing on like responsive and also WS messages WebSockets. So if there were any listeners of any type, we're just going to send it out as a string with a is there a new line added to this? Yeah, you can see it's $content and then a new line. So it's going to print a new line. So if I do channel as test, see, you can see it's streaming in over there. And so, like, how easy was that? All right, so let's get back to the slides when I figure out how to get out of here. All right, so that was HTTP. Grip also works for WebSockets, though. And so the way this works is the backend negotiates a special grip extension. And so what it's basically saying is, I want the proxy to take over and allow pushing to be injected into open WebSockets. And then the backend can actually send control messages over that connection between the proxy and the backend. So unlike with HTTP, where the backend only has one opportunity to speak, a request comes in and the backend just says, okay, stream mode, here's the channels, done. Like it can't talk again because it's HTTP. With WebSockets, the client or the backend can actually talk multiple times to the proxy. It can add channels and remove them. And so the way that the differentiation is done is there's just this simple 2-character prefix. If a message begins with a C and a colon, it's a control message. If it doesn't, then it's a regular message. Or sorry, if it's an M colon, it's a regular message. So pushpin will strip off those 2 characters, and if it's a regular message, it'll ship it down to the client. If it's a control message, though, it'll interpret it. And for example, one type of control message might be subscribe to a certain channel, like channel test. And then when it comes time to publish, the publishing is very similar to publishing for a stream. It's just another format type. And you can actually include more than one format, like that script I was using earlier publishes to multiple formats at once. If different listeners should see different, the data should be represented differently, depending on, maybe it's not JSON that comes out of the WebSocket. It's kind of up to you. And also, this crazy thing that pushpin will do is it'll convert traffic from WebSockets to HTTP. And you might think this is a bizarre thing to do, but actually it's pretty handy because it reduces the number of sockets between the proxy and the backend. So let's say you've got like 1 million connections. This way there's 1 million connections to pushpin, but there's not 1 million connections from pushpin to the backend. But you can still have a WebSocket. And so the way this works is that as messages come in from clients, it's encapsulated into requests using these various events. And the formatting is very similar to chunked encoding, which I'll show you in a second. And then there's no long-lived connections to the backend. Which also allows you to bridge it to kind of whatever you have. If you've already got like a thread pool-based system that's like RESTful or something, you can easily support a WebSocket with that type of architecture. Or if you have an API management system like Kong or something, or 3Scale in there, like you can just put this in front. Whereas those systems would like have no idea what to do with a WebSocket. And so let's see. The drawback, of course, with this is that the server only gets to speak when it's spoken to. But it turns out that works out okay. Typically, when you're building a WebSocket protocol, you tend to have RPC and PubSub. So with RPC, the server has an opportunity to speak every time the client speaks. And then with PubSub, that's usually sort of some spontaneous event, and you can publish that instead. So here's how the conversion protocol works. We've created a new content type called WebSocket events. And so when somebody tries to make a WebSocket connection to an endpoint, this is what gets sent over to your backend from the proxy. Just this open with a character return and new line. Not literally those 4 characters. It's it's just 2 characters. And then your backend can respond with various events as well. So this response here is saying, okay, I'm going to send an open event back. That means accept the connection. Here's a text message with 5 characters, hello. I'm also going to close the connection, and maybe you include like a status code in there. So you can send as many as you want, but you can only send it in reaction to an event that just came in. So let's try this now. All right. So, wow, that's awesome. Am I missing borders on my... Wonderful. Jeez. Sorry, guys, my terminals are misbehaving. All right. This one doesn't need to be big. I'm just going to run pushpin over here. Jesus. All right, let's get another window open. Okay. So I've got another script in here. Let's see, what was it called? Test WebSocket. So this script just reads the request body and then sends it back with the right content type. Now, this is actually enough to create an echo service, believe it or not, because if an open event comes in, the way you acknowledge the connection is by sending an open event back. And you send a text message comes back, send close comes back. So with that in place, if we do this, so there's actually a cool command line tool called WSCat for WebSockets. And if we connect to this script, connecting to a PHP script, we have an echo service. Now, there's no push here, so let's do that next. So there's another script. Let's see. Test grip WebSocket. So this one's a little more complicated. It's still reading the entire request body and setting that content type. And it's also echoing it back. So we do have the echo service, but what it's also doing separately is if it notices that the request contained an open, then it's going to make sure it sets up that grip WebSocket extension here. And then it's also going to set this subflag so that after echoing, it's going to send a control message to subscribe the connection to a channel called test. So if I connect to this instead, it's still an echo service. But now, if let's see. So you remember this, this script here, still use that same one. And so you can see it injecting messages into that WebSocket connection. And then, so there's a couple neat things about this. One is the fact that you don't actually need Apache running. Because it's not in effect right now. Pushpin's the one holding the connection open, so you can actually still publish to it. Now, if I tried to send a message, I would lose the connection. But as long as I turn Apache back on in time, then the echo service still works. So the backend becomes stateless. Here we have a stateless WebSocket service with PHP. So you could even modify the code and not disconnect somebody if you wanted to change the behavior. All right. Now that you understand what you can do with the WebSockets, I'm going to sort of tease you with what we've done with Django, because there's even more magic happening here. But essentially, we created a middleware that parses out that events format and can also, repack it on the way out. And so there's this endpoint here, and it's running a WebSocket system. So if an event came in and it's wondering, was this an open request? You can accept it, and you can say subscribe to this channel, and then you can return. Whatever you return here is kind of bogus because it's just going to get rewritten by the middleware. But in this way, you can actually add a WebSocket endpoint in the middle of a Django app, and handle RPC and handle PubSub, and it's all stateless. So this WebSocket context, that WS value, it's fresh every request. So there's no state here. Even if the first request says it's opening and the second request says it isn't, you didn't get the same object again. Could be on a different box. Maybe you have 2 instances of this Django app. The second one is handling the RPC call, while the first one handled the open request. So it's kind of a wild.
Can I jump in?
Yeah.
Okay, so it's stateless, which is awesome, but I need state.
Why do you need state?
Because I need to know which user.
Okay, so
can we handle it by channel?
So what you can do with this is, and it's not really described here, but you can actually reply with state information, like variables, that pushpin should have. So for example, let's say you've got a WebSocket auth process. So you connect first, and then maybe the user says, here, I'm authenticating, here's some authentication packet. And then when you reply to that saying you are authenticated, at that moment you would also reply with metadata saying user is Justin.
Because that's what my session cookie or whatever.
Yeah, and so any future HTTP request that comes from the proxy will have that metadata on there so that you know it's that same user.
And pushpin is keeping that, so basically,
And-
that's state pushpin.
And because the WebSocket is always tied to one pushpin instance, it's always going to be the one that sends the requests to your backend, so it'll always have the metadata. There won't be this issue where like a different pushpin doesn't have the metadata because the request.
It's not staying across the region.
Correct. So if they lose their connection and they reconnect, they have to re-auth, which will cause you to then assign the metadata again. And yeah, that's actually fairly new, so it's not even in the Django library yet, but yeah, we wanted to make sure we could handle that. Another thing we do is we put a connection ID header on every request, so you know that the same set of requests are actually associated with the same client if you want to like put that in a memcache or something and keep track of it. But I think in a lot of cases, it's best to always avoid it if you can, and then there's always the metadata. Okay, and I mentioned that there's compatibility with API management. It's great because you can just put it right in front of whatever you're using. And in the WebSocket conversion. So, and I want to show a real world example. So, what? Is this big enough to read? Am I like? Anyway, so CBIX is Canadian Bitcoin Index. I mentioned them earlier. They have a streaming API. They also have a WebSocket API. If you highlight up here, you can see their docs. And so. And you can see here they did kind of a Twitter-style API. So they, well, first of all, they have their own domain name, streaming.cbix.ca. They have this new line delimited JSON format. And then they have these various endpoints like index, which is like the value, and then trades if you want to see what like activity is happening in Bitcoin. And they have these JSON payloads. And what's pretty cool about this is that they're using pushpin to power this. So the backend is a Laravel app. It's not really built for push. It's PHP that they have over there. But they get basically a high quality API that you would expect from like Twitter or something. But it's a Laravel backend. So pretty neat what you can do with that. And they also have a WebSocket API because why not? It's like not that much harder to do that with this system. In fact, they even have like resource-oriented WebSockets, which is kind of neat. And then what we end up with though is that Realtime is not this special thing anymore. You don't have to it's not this crazy coding. You don't have to use event-driven frameworks or switch to Node just because you want Realtime. This works with any web framework, any endpoints for any reason. Maybe a query parameter causes something to become a stream. It's like whatever you want. You don't have to have split worlds. We did that at Livefyre. We had Django for REST and Tornado for our streaming API, 2 different code bases. Even though they were both Python, they were still very different. One was thread pool, one was event driven. Same guy did not maintain both. There was some code reuse, but you had to be careful. You don't need to do that anymore with this system. You can put it in the same place. And it leverages pretty much everything you've already built if you have an API stack. And a final plug about Fanout, we like to help people with the real-time APIs. And a big thing about our approach is that our code is open source. So you can always check it out. And in fact, you should at pushpin.org, and tell me what you're building. I want to make sure that this actually works for everybody. So thanks guys. So I don't know if anybody has any questions. So the question is, how does it scale? So it's pretty easy to horizontally scale because the instances don't talk to each other. And we've tried very hard to make sure that they don't need to. Like in the case of that metadata situation, it just kind of works out that they don't need to talk. And so you can just add as many as you need. We've done about, I think the most we had connected to one instance was maybe like 50,000 connections. I bet we could go higher. We haven't done a benchmark in a while. But it's easily horizontally scalable. So you should have no trouble getting to whatever number you need to.
I have 2 questions. One, what is pushpin built in? And 2, what are mobile apps usually using? Like, which of those 4?
Yeah, so first, what is pushpin built with, or how is it made? So it's a C++ app, and it's actually a 0MQ microservice, so it's kind of this crazy project. But I don't know if you guys know the Mongrel2 web server, but it uses that for input. And it's actually set up with, it's 5 different processes. So one handles HTTP input, one handles HTTP output, one handles proxying, and one handles pub/sub logic, and one is just like a launcher that runs the whole thing. But yeah, it's just basically a mix of C and C++ components that communicate via 0MQ. Mobile. So typically, mobile apps push, well, it depends on your app. So there's a lot of Apple Push and Google Cloud messaging being used to push to mobile apps. And there's a couple of reasons for that. I mean, the main one I would say is because you can always reach the app. Like maybe your app isn't even running, but you can use Apple Push to reach it. So you kind of have to use those systems. But you probably wouldn't want to use those for anything that's highly collaborative. So if you're building Google Docs or something like that, you would want to have an open socket for that. And I know some sophisticated apps, what they'll do is when the app is open, they'll be using some kind of long-lived connection to a server. But when it's shut, or you just want to tell a user that something interesting happened, then that's when you'd use push notifications. So mobile apps tend to have a hybrid in there. So there's a couple ways to deal with it. In the case of, when you have that conversion from WebSockets to HTTP, there's actually a disconnect event that you'll get. But in many cases, you may not care. and I don't think using TCP connection validity as a basis for presence is very useful because of timeouts. In other words, or ghosting. So sometimes it might take a very long time for a TCP connection to register as disconnected. So it's often better to have some kind of heartbeat from the client.
Searching for events where eventually
Yeah. Oh, and another thing you can do with that. So this is about detecting disconnects. What you can do instead is you can actually detect subscriptions. So that's another thing you can do. So Pushpin will emit events whenever somebody, at least one user, is listening to a channel. So if you have, let's say you have 1,000 people listening to one channel, as soon as the first guy does it, you get an event. The next 999, you don't get any events. But once they all leave, then you get the unsubscribe. And sometimes you can use that. So if you have you're searching for something and there's some back-end processing, you might wait for the unsubscribe versus the disconnect. And the difference is, I don't know, I guess it's just a preference. Depends on what you care about. If you think you might share, then the channel subscriptions might be better for that. Cool, guys. Thanks.